Suppose two gyroscopes measure the same rotational motion, but one starts recording slightly later than the other. We obtain two signals, y1 and y2, each sampled at their own time vectors t1 and t2. Our goal is to estimate the time delay between them. We'll walk through a three-stage algorithm. First, a coarse search to quickly find the rough neighborhood of the delay. Second, a fine search using small steps and interpolation. And third, a parabolic refinement to pinpoint the minimum with sub-step precision. When the correct delay is applied, the two signals align perfectly, confirming we found our answer. In the first stage, we forget about time entirely. We treat y1 and y2 simply as arrays of numbers and slide one past the other by integer index offsets. Because we skip interpolation altogether, we can scan a very wide range of shifts cheaply. And by sweeping the full range, we're far less likely to get trapped in a local minimum. At each offset k, we compare y1 at index n with y2 at index n minus k, using only the indices where both arrays have data. Let's see what this looks like on the actual signals. We evaluate the cost over a range of integer shifts, from k equals 8 down to k equals -8. We begin at the rightmost shift and scan leftward. At each shift k, we compute the mean squared difference over the overlapping samples. Dividing by the number of overlapping points prevents the cost from appearing artificially low at large offsets where fewer samples contribute. We find the index offset k star that minimizes the cost. To convert from samples to seconds, we multiply by ts, the average time between consecutive samples, giving us a rough time delay estimate. We also keep the cost values one step before and one step after k star. These 3 points at k star -1, k star, and k star +1 define a one sample wide bracket. The fine search will zoom into this window next. In the second stage, we search within this window using a much smaller increment, the step size, which is typically a small fraction of ts. At each fine shift, the shifted time points generally fall between the original samples, so we linearly interpolate y2 to obtain values at the required positions. We then compute the sum of squared differences as before. Again, we identify the shift that minimizes the cost. But rather than accepting this discrete minimum as our answer, we extract 3 key points: the minimum and its 2 immediate neighbors. 3 points are all we need to fit a parabola, a second-degree polynomial that models the shape of the cost function near its minimum. We write 3 equations, one for each point, and solve the resulting linear system for the coefficients a, b, and c. The vertex of the parabola, its minimum, is found by setting the derivative to 0. This gives us s star equals -b over 2a. This is our estimated time delay, delta t. Notice that the parabola's vertex falls between the sampled cost values, giving us a resolution finer than even the step size itself. Each stage narrows the search from the entire shift range to a one sample bracket down to a single sub-step accurate point. Coarse search finds the region. Fine search with interpolation pinpoints the neighborhood, and a parabolic fit extracts the exact delay.